Good evening. This is Professor Shina presenting the pre-recorded chat for the course MECH.5710 Quality Engineering, Week 9. In this week, we'll be talking about tolerance analysis. So, tolerance analysis is a subject that's usually handled by a senior engineer. And the idea here is how to apportion the specifications. So in many designs, you might have a specification for an overall system. And then you have individual specifications for each component of the system. And it's the job of the systems engineer to allocate the resources, allocate the specifications within each subcomponent in order to meet the final system. An example, let's say in BAE Systems, which is a company north of here in Nashua, New Hampshire, which does a lot of electronic surveillance and airborne systems. So for instance, one of the systems it has is to identify another aircraft as a friend or foe, and you might have a specification for 4 seconds in order to identify the aircraft. So that there's several subsystems of radar interception, radar signature, comparing the signature to stored data, and then identifying whether this is a friend or foe aircraft. And the systems engineer then has to balance the different systems in terms of how to allocate the 4 seconds specification into the subsystems that make up the identification system. So I'm going to give it to you in terms of mechanical parts. After all, this is a mechanical engineering course. And this is a typical problem you see in design. And the idea here this week is we're going to look at it in terms of traditional design, which looks at worst case studies. And now the new idea is of using tolerance design. And the idea behind that is use advantages of the normal curve to allow for certain situations where we can design to a much less rigorous specification. And I'll give you examples of that in the lecture and also in the homework, which will give you some insight into how these techniques and tools can be used in modern design. A lot of it drawn from my own consulting experience with different companies around the area. And we'll see what these situations led to and how you can work out the kinks of the design in order to satisfy the design intent. In this particular case, and that's a theoretical case. In fact, I wrote about that case in my first book, Concurrent Engineering. And the idea behind this is how to design this in a worst case versus tolerance analysis. And this is very similar. If you look at the when Japanese cars came to this country, consumers marveled at their great specification in terms of fits of doors. Doors fitted really well in Japanese cars when they were first imported in this country, as opposed to the American cars. And the secret was the difference in terms of specifications between the two different countries. So if you look at this particular case, in this particular case, we have 3 blocks, each with its own specifications. So block 1 has a width of 1 inch plus or minus 10 thousandths. Block 2 has a 1.5 inch plus or minus 5 10,000ths. And block 3 has a specification 1 inch and 375 plus or minus 0.12 inches. So the question becomes is how do you spec the cover for the 3 blocks? And the traditional way of specification the cover is to make sure everything fits. Okay, so the idea behind that, let's say if you're selling a car and you're selling spare parts, you want to actually make sure that as you ship out spare parts, the spare parts will fit into the car. So we'll look at the worst case analysis, WC analysis first. So what we do is we look at each part. Here's part 1, and we look at the high and the low for each part. It's plus or minus 10. So the high is 1010 and the low is 0.990. Same with the second part and the third part. So we add up the parts, we add up the nominal dimensions, which is 3875, and then we add up all the high numbers and all the low numbers. So when we added up all the high numbers, that will be our minimum cover for the 3 parts. Okay, so I'm calling the cover a box. So the box dimension has got to be slightly bigger than the maximum tolerance of the 3 parts. So we give it a clearance to make sure it doesn't, it's not snug. So if the highest high tolerance of all 3 parts is 3.902, we add 1 more thousandths, 1 more mil, and we have 3903. Let's make that a little bit bigger. 3903. So that's the minimum spec of the box. This way the box will always fit. The cover will always fit. Guaranteed to fit. Because we have a clearance, we take the maximum, and we have a clearance, worst case design. Then we look at the minimum, the corresponding minimum. The corresponding minimum is 3848. And the corresponding other side of that spec, we have to have, that's the minimum spec of the box. It's 3875 nominal, right up here. And it has 3901 as the minimum dimension, and we're going to apply some tolerances to that. So let's say we apply plus or minus 5, which is 10 mils, so it's 3913. So now we have a gap between the box and the parts, and the gap goes from 1,000, which is the clearance by design, by worst case design, and then we take the maximum box, 39013, which is minimum box plus 10 thousandths, okay, because we took a tolerance of 5 thousandths. So we have a gap whose minimum 1, whose maximum 65. And that gap is the gap I was talking about in the car doors. So as you design the components of the car door and the way what they call fit and finish, the way the door closes on its hinges, there's a big gap because the average gap is 33. Okay. Now, what is the response of the design department for situations like this? The usual response is to tighten up the tolerance. So if we tighten up the tolerance, let's say instead of 005, we tighten up the tolerance to 002 for each part. So we do same calculations again. We end up with a nominal, which is the same, but the tolerance, the high number is 3881, okay, which is again, 3881 is the addition of the high numbers, so 3882, and then we go plus or minus 2 thousandths. So so this is the minimum of the box. This is the maximum of the box, which adds up all thousandths, so that the average now is from 001, which is what we had before, but that the gap has decreased to 17, which is 3886 subtracted from 3896. So the gap has become smaller, more tolerable to the customer. But it's cost money to have more tolerance or tighter tolerance on the parts. So is there another way of thinking about this? Okay, so one way of thinking about it is, well, let's say use the normal curve as opposed to a worst case analysis. We can tolerate some failures. So in this particular case, we're looking at the same design, only this time we're going to present it in a tolerance analysis way. So what we say then is that each plus or minus represents 3 sigma. And then we divide by 3, and then we get the, if we assume the design is 3 sigma, then 1 sigma is 0033, which is 1/3 of the tolerance. So we assume that the tolerance is 3 sigma, and then we divide by 3 to get the 3 sigma. We get the 1 sigma. So for the box, which contains all of the tolerances are added. So instead of adding them algebraically, we add them in a normal fashion. So what we do is we add up in the sigmas. Now, if you remember, I said earlier in the course that the sigmas add up in the squares. So what we do is we take each sigma, square it, and then take the square root, and that would be the 1 sigma of the box, of the cover. So if we're going to have a 3 sigma, at this point, plus or minus 1 sigma is equivalent to 68%. Plus or minus 2 sigma is equivalent to 99% of the parts will fit, and plus or minus 3 sigma is 99.74% of the parts will fit. So if we use 3 sigma design, which is, we already know the sigma of the box, which is sigma of the system, then plus or minus 3 box sigma will cover, which is plus or minus 0.16, will cover 99.73% of the part. So the reject rate based on design, on 3 sigma design, is 2,700 parts per million. Maybe that's too much. Maybe we go to 4 sigma, we drop that to 32 parts per million. Remember that this is one-sided. The problem occurs when the parts don't fit. Okay, so it's really, if the parts are too small, that's not a problem. It's only a problem if the parts are too big. So this is a one-sided spec, not a two-sided spec. So when I said 1 box sigma, it really is, or 3 sigma design, it's really not 2,700, but it's 1350 reject rate. 1,350 ppm, because it's only rejected on one side. Okay, so that's the difference between the two. So now we can go to companies, or we can design parts, and we can say, okay, we'll design it to 4 sigma. If we design it to 4 sigma, 32 parts per million will fail. We can tolerate that, but we get a much better specification. Like this 3 sigma design is 0.16. We go back to the previous one, and that's so much better than the worst case design, which is much more heavier in specifications, because we can take, we don't have to reduce the tolerance to 0.02. We can essentially reduce the tolerance to 0.05, no problem. Okay, so that's an example. So this is another way of presenting it. Essentially, this is the gap, and you can see the gap is only one way. It's not both ways. It's only a gap if it's lower than. If it's greater than, if it's lower than, it's okay. There's a gap, but it's not an interference fit. But if the parts are too big on the large side, then there would be interference. In a system where we have also the sigma of the box, we're going to count all the components of the system, the 3 parts and the sigma of the box. So it comes up a little bit higher because we're adding the box. So instead of 0.054, now it's 0.057. And the nominal is the same, okay? That's the beauty about it. The nominal is the same. The only difference is the gap is 4 sigma. And we can estimate the failure rate on the Z-chart as we all know it. Now, one more thing is you could do in this particular instance, and that is, in this case, we divided up the spec into 3 to get the 3 sigma, got the system sigma, and then multiplied by 3. Well, you can take away the division and the multiplication. You can take the specification as is, and that'll work for every sigma because the math is the same. So instead of saying, well, this is 3 sigma, we have to divide by 1, add up the sigmas and the root mean square, you get the sigma of the system, then multiply by 3 again. You can just take the tolerance as is, and that would be for any sigma design, that would work. Okay, so let's look at another example. Now, this example was from a company in Andover. They came to me and they said, we make a chip, a power supply that's in a chip. So rather than build a power supply, we can build a power supply on a chip, and therefore you can power your device right on the printed circuit board. So the problem is they needed to test the chip. In order to test the chips, they have to put the chip on a test stand with many pins in it. Sometimes these pins are spring-loaded to access the power points on the chip. And the biggest problem, they was facing the same problem that we looked at in the parts and the box. In order to make it work, they had to come up with extreme tolerance, very tight tolerances for the pins. Is there any way we can make it better? Well, let's try. So if we look at the pin, which is here, it's a nominal quarter inch, and it's trying to fit into a pad or a hole in the printed circuit board, which is 260 plus or minus 0.06. So there's the differences in the pin end versus the target, which is the pin, which is the pad, of 10 thousandths. Okay, so we can do the worst case analysis the same way we did it before. We say the 250 pins are mating to holes. Just make it holes instead of pads is better. Hole diameter is 260 plus or minus 0.06. What is the worst case pin tolerance? Okay, this is the way we do it. The smallest hole is 254. It's 260, which is the nominal, minus the tolerance, one-sided tolerance, is 254. We got to allow for a clearance, so it came out to be 253. The largest pin, that's going to be the largest pin in order for the pin to touch the hole, to go inside the hole. So that is 253. If the pin, that's 3 mils away from the nominal, so therefore the tolerance of the pin cannot exceed 0.03, or it's not going to fit in the hole. Okay, so that's the worst case analysis. We need 0.03, and that's kind of, these pins are machined, that might be a little bit expensive. Can we do this in a tolerance analysis way? Let's look at it. We can do the same thing. Sigma of the hole is 0.02. It's let's assume 3 sigma design. So the sigma of the hole is 0.06 over 0.02. So the gap between the hole and the power and the hole and the pin, the gap between them is 3 sigma of the system. Now, if we're going to try to balance the sigma of the system, because we already know what the sigma of the system is, okay, because the sigma of the system is all the different sigmas, right? So we say the sigma squared of the system, because the sigma is always equal in the squares. Sigma squares of the system is sigma squares of the holes and sigma squares of the pin, okay? So essentially what we say then is the difference between the hole and the pin is 260 minus 250. 260 is the, remember, we're all doing here as nominals. 260 minus 250, it's 3 sigma design, which is divide by 3 squared, okay? So that gives us the sigma squared of the system. Okay, that gives us the sigma squared of the system. So the sigma of the system is sigma squared of the hole and sigma squared of the pin. Okay, and the difference, the system consists of this hole in the pin, so we know the difference. So sigma squared of the pin is sigma squared of the system minus sigma squared of the hole. Okay, so sigma of the pin is the square root of that, and that is 0027. So what is the tolerance? The tolerance, of course, is 3 sigma design. It's a 3 sigma system. So it would be 3 times sigma of the pin and comes out to 008. So guess what happened? If we did worst case analysis, we get 003, and the pins will always go in the holes. If we do a 3 sigma design with a pin tolerance of 008, much cheaper to make, the reject rate is equivalent to one-sided reject rate. If the pin is too small, that's no problem. It'll fit into the hole. If it's too big, that's when the problem is. So the reject rate is 1350 parts per million, or 0.135%. Very small number, and you could tolerate it. You can even do it as 4 sigma without a problem, and the reject rate will be only 32 parts per million. So the RMS method is a method that allows you to open up the specifications, the tolerances of the specification, and the penalty, of course, is that there is a slight number of rejects. We do not guarantee that every part meets the specification, or every part will mate where it's going to be. Okay, so the difference here in the worst case analysis, we're looking at maxes and mins, right? We're looking at the differences between maxes and mins. When we do statistical tolerance analysis, we're looking at nominals between the between the pin and the hole. We're always looking at the difference in nominals, and then we're looking at some kind of reject rate based on the z-curve. Okay, so statistical tolerance analysis is essentially translating mins and max to numbers of sigma, okay, which allows you for much better, easier specifications to meet, easier tolerances to meet. Here's a third one. This was a medical company. So this is one of these catheters that goes into your coronary artery and then blocks a blockage in your heart, in your coronary artery. And it does that by vibrating. And by vibrating, it's very important, for instance, in things called thrombosis. Thrombosis occurs when you, let's say, sit on a plane for a long plane ride. Let's say flying to Australia, it's 14 hours from Los Angeles to Sydney. And your blood, if you don't move around, and a lot of people just sit in their seats, if you don't move around, there's chance of creating blood clots in your legs. And that's very, very dangerous, because these clots can form and they can travel to your brain and give you a stroke. So there's been a lot of development on clot busters. Of course, it has to be done in a very, very accurate way, so that when we bust a clot, the pieces that come out of there are going to be very small. Otherwise, they're going to go all over your body. And the most danger is in your brain, because it's going to go into your brain and block an artery, and then there's a stroke. So this is a particular company that was designing one of these catheters, which end up in a kind of a rotor kind of design. It vibrates to unblock the blockage in the arteries, or the blockage in the leg, which is the one you get in thrombosis for long flights. So one of the problems they discovered, and that's why they called on me, is that they had a design that is interference design. Actually, the parts, if they built a specification, will interfere with each other and will not be able to assemble. And they were concerned about that, and they wanted me to look into it. So I made a simulation of the head of the catheter, and what you have is you have a cylinder, which I call a barrel, and there's a wire wrapped around it, and that makes for the vibration, and a cover for that. Okay, so essentially you have these three specifications. Remember, this is going in your heart, so it's pretty small numbers. The barrel OD is 0075 plus or minus 2/10,000. Then you get a winding wire on both sides, which is 0027 2/10,000. And then the cover is 136 2/10,000. If we do the analysis in the worst case, the maximum barrel essentially is 0075 plus 002 is 0077. You add to that two maximum wires. So you have to visualize what you're analyzing. So you need to know whether you're going to add or subtract when you look at the mins and the max. In this case, you're looking at the maximum barrel, the maximum wire running two times, and the minimum cover. That's the difference. So the maximum wire is 2 times 29, which is 29 is 27 plus or minus 2/10,000. So that's going to be 0058. So if we add up 0077 and 0058, we get 0135. Okay, so the maximum wire is 0.0135. The minimum cover is 0134. Okay, 0134. So we get 0135 from adding the maximum barrel and the maximum of two wires, which is 0135. The minimum cover is 0134. This is an interference fit. That means theoretically, worst case analysis, these parts will not fit. So I was called in to see if I can analyze. I was actually giving them the scores. And they called me and I said, bring in some interesting problems from work. We can work on it. So this is an interference fit. The cover will not fit. The minimum cover will not fit the maximum barrel, the maximum wires. There's a problem. Do we stop production? No. We'll look at it in terms of what is the expected reject rate. Okay. So in order to find the expected reject rate, we have to determine the Z. Okay. So the Z comes out. We need to, in order to find the Z, we need to know the gap. That's number one. So what is the gap? And in terms of average and also in terms of sigma. So the average of the gap, as I said, you have to look at the picture to find it and see how it works. 136, which is the cover, nominal. Everything in the average of the gap is nominal. 136 minus the barrel minus two wires, that is the average gap based on nominals. Not based on mins and max, based on nominals. Mins and max only for worst case design. Nominals is for statistical analysis or tolerance design. 070, and we looked at the sigma of the gap based on 4 sigma design. So essentially what we have is since everybody is 002, every component is 002, there is 4 of those. So you take 002 over 3, that's a 3 sigma design, times 4, there's 4 of them, you get 00133, or triple aught 133. So the Z is, you do Z at x equals 0, because that's when the two mate exactly. This is the average nominal of the gap. Nominal of the gap 70. The standard deviation of the gap is 13, and we found that by root mean square of the individual component sigmas. So it turned out that this is a 5.25 sigma design. The average reject rate is 0.3 parts per million. So if you're making catheters, a human, and this is an issue because you want to have a tight fit, that 0.3 ppm, 1 out of 3 million will not fit. And that will not fit in production. So that is not a big deal. And we want it to be very snug. We certainly don't want the cover to come off as the catheter vibrates. The catheter heads vibrate. So that's another interesting way of using tolerance analysis as opposed to worst case analysis, and then predicting the reject rate beforehand, something that the company can tolerate or the designers can tolerate. This is a problem that I turned into. I worked with this problem with British Airways, British Aerospace Company, BAE, British Aerospace. But anyhow, they call it BAE system in Nashua, New Hampshire. And again, I gave them this course, and they wanted to compose some problems that they can train the mechanical engineers. So essentially, they were designing a cooling system for 30 watts. Right now, they use the surface mount technology components with a composite made of thermal conduction and 2 fans in the unit. So essentially, you have a electronic unit in the cockpit of an airplane, and you need to take the heat out of the electronics. So they use a composite core, which takes away the heat, with 2 fans in the box. And one way is to look at the design alternative. Can we change from composite to aluminum? Is that possible? What is the impact of that? We save $450. Or we can eliminate 1 cooling fan. We save $150 per fan. What are the implications? Not that we're going to do it. Nobody's going to change the design on something that's already flying. But just as an exercise to understand, if we save some money, what's the impact on reliability? Now, I translated this into a problem in the homework, but essentially that's the analysis we went through. Essentially, what we know is the junction temperature inside an IC. An IC is made of millions of transistors, and there's a junction temperature at the IC, and there's a spec associated with that. They don't want to go over 100, okay? 100 degree F. You don't want to melt the solder in that junction, so that would be a disaster, right? So essentially, we worked out with the mechanical engineers how the temperature is going to go. So you start with air coming in at 55 degrees, and then it just, I guess this would be F, not C, actually. And then it gradually the temperature raises as it goes through different components in the box, in the electronics box. The chassis has some conduction. It goes to the board edge, which can be measured. Composite core drops it some more. Conduction through the PC, through the attachment of the component. This is what they do is they weld these gold wires between the chip and its packaging. So there's heat loss through that, heat rise through that, and then the case to the junction, and then you finally arrive at the junction temperature. So they did a worst and best case analysis. If you think about this, this could be upper spec limit and lower spec limit based on that. So we went through all the design steps, all the analysis, thermal analysis, to go from inlet air to the junction temperature for transistor on the chip, because that is defined, okay? And we don't want to melt that, that's for sure. So we went from 105 upper spec limit to 87 lower spec limit. So typical system performance, instead of getting 100, upper control limit of 105, and lower control limit, upper spec limit of 105, lower spec limit of 87, we get a typical system of 96 with 1.2 degrees plus or minus. So if we do 3 sigma design, we get 100. If we do 100 junction temperature of the transistor. If we do a 6 sigma design, we do a 103 temperature, and I'm going to have a homework like that there. And then the worst case design, which is what we have right now, is 7.6. So 7.5 sigma gives us gives us something like 103 junction temperature, and 3 sigma design gives us 100 degrees temperature. Okay, what if we substitute core from composite? The core would be from composite to aluminum. Worst case on the 7 degrees centigrade becomes 12 degrees. So there's the 7 degrees. It becomes 12 degrees. We do the calculation again. So the best are 91 and the worst is 110. So instead of looking at that, would be 110 and 91 over here, okay? Because we get better, less temperature rise with aluminum. Well, excuse me, more temperature rise with aluminum. And if we use aluminum, we end up junction temperature on the average of 105 and 3.5 sigma. Same story if we eliminate the cooling fan. So essentially, we can begin to understand what option we have. We're not going to do changing. We just wanted to know what the options we have if we wanted to drop from a very worst case design analysis of 7.5 sigma. Can we drop it to something smaller than that, and we can get 3.5 sigma? Maybe tolerable, but certainly in a jet airplane, which has cost $50 million, and the pilot's life is worth hundreds of millions of dollars, they're not going to worry about $350 cost for an additional fan or using composite core instead of aluminum core for the printed circuit boards to get better junction temperatures for the transistors in the printed circuit boards of the design. Okay, the mic went out, so I just want to make sure that the summary of what I was saying is we can analyze the design, whether it is made of, whether we can reduce the sigma of the design by using not so expensive material or eliminating some fans, and that the design will drop from 7.5 sigma to 3.5 sigma. But at the same time, we are risking a $150 million plane and hundreds of millions of dollars of training for the pilot if we lose the pilot as well. So this was an exercise just to understand what is the difference between gold plating design and not gold plating design. Okay, so that's really what I want to say on tolerance analysis. And then I want to go over it with you in terms of the homework that I have made for you. And I'll discuss that homework in the live chat as well, but I wanted to give you a heads up on what I'm trying to do in the homework. So to summarize, we've given you 3 case studies. 1, using the blocks and looking at the tolerance for the cover or the box using worst case design. And the only way you can make that manageable in terms of the gap that's made between the box and the parts by reducing the tolerance to 2,000s, and that's very, very expensive. So we can do that with tolerance and tolerance design. Then gave you the other example of pins. They have to go into holes or mate with holes. And that worst case analysis is 003. And we can go to tolerance analysis with 008. That's 3 sigma design. And we can tolerate 1,350 parts per million analysis. And the third example is this if this clot buster that we can use for treating thrombosis, and that the design itself is a interference design, but the reject rate is very manageable at 0.3 parts per million. So that's going to be okay to do that as well. So these are the three examples I gave you. What is common about these three examples? I think it's best demonstrated by the pin here. When we do worst case analysis, we deal with the specifications, the largest pin, the smallest hole. So we deal with the end specification. When we do tolerance analysis, we deal with sigmas, and sigmas add up in the squares. So we use sigma of the system and the gap that's being produced, and then we can translate that into reject rate using the Z distribution. So I showed you that in every instance. So we'll take a look at some of the homework problems that I'm going to discuss with you in the live chat next week. So let's take a look at the homework. The first one is something I used to have when I used to work on early computers. When there was no integration, when there was no large ICs, all computer electronics were put into cards, computer cards or PC board cards, and they have computer racks where you plug in these boards. So you have the rack, what they call the card cage, and then you have slides where you push the PC boards in, and the PC boards go into the slides. So I made an example or a problem to take a look at a system of three parts. The card cage, which is 19 by 11, 19 long, 11 in depth, and 525 in height. And the spec on it is plus or minus 10. Then we have two slides. And they're also 11 because they go the full depth of the card cage of 125 plus 005 top and bottom. So you have two slides. And then the PC board itself, it also goes down to 11. The question becomes, is the PC board comes in, we want it to come in plus or minus 20,000 because that's the normal industry standard for routed PC boards. What should the nominal PC board be? That's the question. And I want you to do that in both worst case analysis and in terms of tolerance analysis. Okay? One answer is very simple. Reject rate, we say CPK 1.33. So that's a 4 sigma design. So worst case reject rate is always 0 because everything is guaranteed to fit. Worst case in statistical tolerance analysis is the reject rate of 133, 32 parts per million because it's only one-sided. So at least you can answer C with no problem. Then we'll take a quick look at how we're going to answer A and B. So A and B is worst case tolerance, and we're going to ask for the tolerance gap, and the tolerance gap in worst case tolerance and in statistical tolerance, and the recommended height of the PC board. That's what we're trying to figure out what to do with the PC board. Problem 2 is a kind of abbreviated question that we just gave, and it's a little bit confusing. So I tried to put in the problem all the numbers that we have. So I'll discuss that in a minute as well. And then problem 3 is a problem one of the Raytheon engineers gave me. And that is, you have an assembly of many components. And we have an assembly that's called a tolerance stack-up. So they had a screw that went through all of them and then would be thread to fasten all the subcomponents of the system. So I did all the calculations for you. all the components, the system, lock washer, flat washer, components, chassis, and the screw. So the screw is working against all of those, okay? And each one of them has a min and a max, 3 sigma and a sigma. And I think we said 3 sigma design, okay? So, so that's why we have the tables of sigma. So I gave you sigma of the system, which is summation of all the sigma squares of the system. And the sigma of the system is 38. So the first question is, calculate the reject rate as currently specified. As you see something like this, what's the expected reject rate? Okay, so where's the gap? The gap is between the screw, which is 110, and all the components that you're working with, the chassis, the component, the flat washer, and the lock washer. So 110 minus those, that would be the nominal, or x bar minus mu, and then the sigma divided by sigma, and that will give you the z, and the z gives you the z gives you the function of z, which is the reject rate. So this is as designed. As the numbers came in, this is what the reject rate is going to be. What happened is they didn't want the screw to be too long because they had electronic components there, and they didn't want to short them out. So the screw was too short. So the reject rate was high, and they couldn't fasten all the components. So that's what you're going to work on for the first problem. The second problem, if you nominally said 3 sigma statistical tolerance analysis. So that's for the screw, okay? So 110 is the screw right now. I'm sorry, 120 plus or minus 0.1 is the screw right now. So if you're doing statistical tolerance analysis, you always deal with the nominals. So essentially it's a 120 minus the nominal of all the other parts divided by the system of 3, how would you re-specify the screw for 3 sigma statistical tolerance analysis? So if you have sigma of the system, 3 sigma statistical tolerance analysis is very easy to find out. And then you find out the reject rate, which would be very easy because that's a reject rate of 3 sigma. Now, if you did worst case analysis, how would you re-specify the screw nominal? So as I said earlier, you re-specify the screw nominal by dealing with mins and max. That's the worst case. So worst case deals with mins and max. Statistical tolerance analysis deals with sigmas and nominals. Okay, they don't deal with mins and max. That's why I want to remind you when you do this problem. So what I've done is I've done a partial solution, which I usually try to do to get you started on this. So the first thing we're going to do in problem number 1, which is, this is very funny. When they tried to push the boards in the early days, they actually gave you some kind of a tool. The best way I can describe it is some kind of a scissor tool where you can grab the board at the end and push the board in or push the board out, because the interference, because sometimes the way the designs came up, there was too much interference and you couldn't pull out the boards by hand. So they gave you a kind of a scissors grabber that you can grab the boards and pull them out. So that was very funny. That's a standard issue to every engineer or technician working on electronic systems involving what they call cart cage or cage racks. And you know, in the old days, this was really funny. So at the end, where the cart cage was, at the end there would be wire wound. There would be pins at the end because the boards will go into connectors, and the connectors will come out in pins, and then the pins are interconnected. And essentially, you'd hire production workers to use these tools that would wrap wires between the different pins. So I remember working on a nest of these pins, like when you see one of the telephone repair people come in and work on the telephone exchange or telephone switch outside your house. It's like 10,000 wires. How do you know which wire is which? When you work on this for a year, it might be 10,000 wires, but you know exactly what each wire does. It's just amazing what when you work on something, what human brains can do. Just like when I watch one of the phone repair people come in outside my house, there's a box, exchange box for the phone. He pulls it out, and there's this net of wires, and you can figure out which wire goes where. That's just absolutely amazing. Anyhow, so the first thing you're going to do is you're going to find out the 4 sigmas, and they're all given up on top. 025 comes out from the let's see, the sigmas are, this is a 4 sigma design, so you're going to take the 10, 0110, divide by 4, 025. Then you're going to take the 5, and you're going to divide by 4, so you're going to get 2, 00125. And the last one is 020, divide by 4, and you're going to get 005. So now you're going to get this system sigma at 57. So we already know the 4 sigma of the gap is 4 times 0057 or 0023. That's the statistical gap, right? That's a partial solution. And therefore, the average statistical gap is 0015, okay? And you compare that with the worst case gap. Okay, so now all you have to do is to tell me the reject rate, which is straightforward. As I said, you know, the reject rate for worst case analysis, worst case design is 0, because that's by design, and the worst case for 4 sigma design is 32 parts per million. We already know that from the table. So the only thing we have to do is what is the z, and then from the z you get the reject rate. But you should get the same number we had before, which is 4 sigma. Okay, so that's a statistical solution. The worst case design is you're going to work off mins and max, okay, and then the gap, which is the halfway between the two. So worst case, you're working with mins and max. Statistical solution, you're working with nominals, plus or minus the sigma of the system, depending on what sigma you have. So these are the way that you would solve this problem. It's not that difficult. For this one, I made it very simple, like the other one. So I gave you a worst case and a best case. So essentially think of that as upper and lower spec limit. And then I gave you, if you take the average of those two, would be 76. That's the midpoint. That's a nominal. But typical, an engineer said, typically I'll get 75.6. So typically when they make the measurements on systems that were designed that way, the average of the system is 75.6 as opposed to the 76, which is halfway between the specs, which is the nominal. So you got a slight average shift. So the nominal would be 76, the typical would be 75.6, and that's the average. So that you do not confuse 76, which is the nominal, with 75.6, which is the average. I showed you that in the map. Said the engineer determines that the desired system typical board edge temperature performance was 76 with a sigma of the system 1.5. So A, given that they have 76 and the sigma of the system is 1.5, what is the worst case design? CPK. Very straightforward. CPK is upper spec limit, okay, which is 80 minus 76 over 3 sigma. Very easy to do. You already have this. You already have the sigma because it was given to you as 1.5. And upper spec limit. So I already solved it for you. Okay. B, if we assume this is a 4 sigma design, for each step, that's the important sentence, for each step. If a 4 sigma design for each step, then there's a sigma for each step. Okay, there's 3 steps. So this one has a span of 4, right? A span of 4, so that the tolerance is plus or minus 2, okay? A span of 4. So if you look between the typical, you look at the typical, which is halfway point between 6 and 10, between typical and one of the worst case designs, or the best case designs, it's 2, the delta is 2, okay? But the span is 4 between upper and lower. Upper spec limit minus lower spec limit is 4. And you span it by 2 so that you are getting a sigma of that step of 1/2, because the span is 4 and your delta is 2. So that's half. And that's the same story here. The span is 4 and the delta is 2. Okay, and that represents 4 sigma. If the design was 4 sigma, then that would be half. Here, the span is 0.4 because 2.6 is the midpoint, is the average. It goes up to 3 and lower spec limit is 2.2, so the span is 0.4. And the system is 4 sigma system, so that span is supposed to be 4 sigma, so sigma would be 0.1. Okay, so now we did all this. Now if we're doing B, all we have to do is to get the sigma of the system from these 3 sigmas using root mean squared. So essentially he said, what's the sigma of the system? Okay, so the sigma of the system is taking each process step, each design step, squaring it, taking the square root, that's the sigma of the system. And what's the CPK of the system? Remember that we are doing it versus data range, which is average performance, which is 75.6. So CPK is going to be upper spec limit or lower spec limit, depending, we're going to be the minimum. So 75.6 is closer to the best case design. So 75.6 minus 71 over 3 sigma. And the 3 sigma is not the same sigma as A. The sigma from A came out from a typical observation of an engineer saying the system sigma is 1.5. But now we're taking sigma from the root mean square of the sigmas of the system. Okay, so so you're going to have the CPK and the reject rate from the CPK. And then I said, typically, if you had a 6 sigma design, what is the expected sigma? If you, as shown, the system with the upper spec limit and lower spec limit, what do you expect if you had sigma of the system? Now we go back, instead of individual components forming the sigma of the system, we go back to the system being 1.5 and a nominal of 76. So you recalculate with nominal of 0.76 and sigma of the system of 1.5. What I tried to demonstrate with the second problem is a 4 sigma design for components of the system. It does not mean that the final sigma, using that technique, it does not mean that the final system CPK is going to be 4 sigma, because it's going to be root mean squared of the 3 process step. It's going to be a little bit different. Okay, so with that, I think our hour have completed, and we look forward to seeing you on the live chat next week. Good night.